Hi everyone. In today's video, we're going to continue our discussion on conjugated pi systems and pericyclic reactions. This time, we're going to talk about the electrophilic addition to conjugated pi systems and look at how we can control this reaction under a variety of conditions, essentially under thermodynamic and kinetic control. It's my goal that by the end of this video, you will be able to predict the products of electrophilic addition reactions to conjugated dienes, and then you should also be able to explain the effect of temperature on the outcome of electrophilic additions to conjugated dienes. So you recall that if you have an alkene like this, and you treat that alkene with a hydrogen halide, such as a hydrogen chloride, bromide, or iodide, you will go through a Markov-Markov hydrohalogenation, which will place the halogen on the more substituted carbon. And the mechanism proceeds through an initial proton transfer to form a carbocation. In this case, your tertiary carbocation is preferentially formed. And then the leaving group halide can nucleophilically attack that carbocation to form your alkyl halide. And it's that first initial step, the proton transfer step, that is both rate determining, but also determines and controls the regiochemical outcomes of the reaction. But what about if you had to do an addition to a conjugated diene? For example, what happens if we treat this diene with hydrogen halide? In this case, two major products are actually formed in the course of this reaction. So why is that the case? Why do we get two products here? So once again, if you start the reaction by treating our diene with your hydrogen halide, the initial mechanistic step is a proton transfer to form this particular carbocation. However, this carbocation is an allylic carbocation, which means that it has a resonance form, and you can actually derive that, which places carbocation character also on that primary terminal carbon. And recall that your allylic carbocation is stabilized by resonance. So now you have two possible positions in which your nucleophilic halide can attack. You can either attack at the tertiary carbon or attack at the primary carbon. So your nucleophile can then attack any of the carbons with carbocation character to form both constitutional isomers of your products. These products are called 1,2 adduct and 1,4 adduct, respectively. So the so-called 1,2 adduct is called that because it comes from a 1,2 addition pathway where the two groups are added on carbon 1 and carbon 2 on the chain. And the 1,4 adduct is called this because it comes from a 1,4 addition where the two groups, the hydrogen and the halide in this case, are on carbon 1 and carbon 4. So to hone this 1,2 versus 1,4 product down, so consider this particular diene again, and we're going to react that with HBr. And we can number our carbons as such, where we start numbering from one end of the diene and you end up on the other end of the diene. Your hydrogen is going to preferentially add to the 1 position, which will put the carbocation in the 2 position. So once again, now you have your hydrogen in the 1 position, and now there's carbocation character at the 2 and the 4 position, which will get you your 1,2 adduct and your 1,4 adduct. Okay, so we're going to now delve more deeply into the energetics of this particular reaction, and we will use the hydrochlorination of butadiene as our example. So if you wanted to predict the major parts of this reaction, you should get the following products, where these are your 1,2 adducts, and this is your 1,4 adduct. Okay? So now let's look at how this reaction will look like on a potential energy surface. So starting with your butadiene and your hydrogen halide, the initial step, as we know, is going to be rate determining. So you're going to first start with the formation of your allylic carbocation and your halide ion. So note that because we added the hydrogen to the carbon 1, that chloride is really close to the carbocation character in carbon 2. So once again, once you form that chloride in that solution, it's at first really close to the carbon 2 carbocation, which means that this reaction can very quickly form that 1,2 adduct. However, the chloride can also move over to the carbon 4 position, which also has carbocation character, and then attack that carbocation. But because it's not that close to that carbocation, the barrier is a little bit higher than the 1,2 barrier. However, consider the alkenes formed from the 1,4 addition versus the alkene formed from the 1,2 addition, and you would see that the 1,4 adduct is actually more stable than the 1,2 adduct because you're forming a disubstituted alkene versus a monosubstituted alkene. And so that energy of the 1,4 adduct will be lower than the energy of the 1,2 adduct. And so that 1,4 adduct is going to be thermodynamically preferred because it's the most stable alkene, while the 1,2 adduct is always going to be faster because of that proximity effect, because that chloride is very close to that carbon 2 upon the carbocation formation. So the 1,2 addition is always faster and kinetically preferred, but in this case, the 1,4 adduct is more stable than the 1,2 adduct because of the substitution patterns of the alkene. And so at low temperatures, so let's say you just have enough energy to get to the 1,2 adduct, but you don't have enough energy to go back from the 1,2 adduct back to the carbocation, the kinetic product is always going to be preferred. So this reaction will be under kinetic control. Okay, so once again, at low temperatures, you might have enough energy to get from the carbocation to the 1,2 adduct, but you will not have enough energy to go back to the carbocation in order to go to the 1,4 adduct. And so altogether, your major product will actually be your 1,2 adduct. At a higher temperature, however, you're going to have enough energy for that 1,2 adduct to go back to the carbocation and then go to the 1,4 adduct and go back. So the 1,2 and the 1,4 adduct will be accessible and reversible back and forth between its product and its carbocation. This would mean that altogether it's going to be the more stable alkene that will be preferred and will be formed as your major product in the reaction under high temperatures. So at high temperatures, once again, you have enough energy to equilibrate between both the 1,2 and the 1,4 adducts. So the most stable product will actually be preferred. So what we call this is thermodynamic control. Okay, so under low temperatures, you're under kinetic control because the kinetic product is favored over the thermodynamic product. And under high temperatures, you're under thermodynamic control because the thermodynamic product is favored over the kinetic product. The kinetic product always come from 1,2 addition, but the thermodynamic product can come from either the 1,2 or the 1,4. It's just depending on what's the most stable alkene. Okay, and so just to kind of help to situate you as you're looking at these types of problems, for hydrohalogenations, when we say something is at low temperatures, we really mean somewhere around 0 degrees Celsius. And at high temperatures for this particular type of reaction, we mean somewhere around 40 degrees Celsius. So let's practice. The hydrobromination of butadiene at 0 degrees Celsius is technically under low temperatures. So that means that you're under kinetic control. And so under the kinetic control, your 1,2 adduct is going to be favored, which means that this is going to be your major products of the reaction. Okay, so take that same butadiene and treat that with HBr again. And this time you want to treat it at 40 degrees Celsius. This time you're under thermodynamic control, and so the most stable alkene is preferentially formed here. The most stable alkene that is potentially formed here is going to be your 1,4 adduct, and so that's going to be your major product in this reaction. Okay, let's try this particular case. So we're going to take this particular substituted diene and then treat that with HBr at 0 degrees Celsius. This means that we're under kinetic control and our 1,2 adduct is always favored at 0 degrees Celsius, which means that these allylic halides are a major product in this reaction. And then we take this same alkene and treat it with HBr, but now at 40 degrees Celsius. And under these conditions, you're under thermodynamic control, which means that the most stable alkene is preferentially formed. But be careful, in this case, the most stable alkene is not the 1,4 adduct, it is still the 1,2 adduct. And that means that your 1,2 adduct is also still preferred under thermodynamic control, so at high temperatures and at low temperatures. And you can convince yourself that this is the case by looking at the alkene substitution pattern of the 1,4 adduct, and you would see that the 1,2 adduct is still more stable because it's trisubstituted alkene versus a disubstituted alkene. Okay, and then lastly in this video, what I just want to address here very quickly is that the addition chemistry with conjugated dienes is very similar for all kinds of electrophilic addition reactions. So another one is if you want to add Br2 across a conjugated diene, it actually behaves exactly like your HBr case, where you get a mixture of your 1,2 and your 1,4 product. And so you take a conjugated diene, react that with a Br2, you can see that you can get these sets of 1,2 products, or you can get the 1,4 product as well. And this means that the mechanism for this reaction must involve a carbocation that can engage in resonance as opposed to your cyclic bromonium intermediate we've learned in the previous semester with just a regular old alkene. So that's a functional difference here. But just keep that in mind that electrophilic additions to conjugated dienes in general, you get the mixture of 1,2 and 1,4 products. Okay, and that's it for this video. I hope that you can be able to predict the products of electrophilic addition reactions to conjugated dienes and also explain the effect of temperature on the overall outcome, whether it's thermodynamic or kinetic control of your electrophilic additions to conjugated dienes. Thanks so much for watching this video, and I will see you in class.